All right, today we are going to look at integration by parts. This is a BC specific topic. So this is not something that you learned in AB last year, and this is almost a guarantee to show up on the BC exam. Integration by parts is the closest thing that we have to a product rule for integration. So here's how integration by parts works. We're used to using U substitution. We're now going to introduce V to that as well. So we're going to be choosing a U, a V, a du, and a dv. So if U and V are functions of x that have continuous derivatives, then the way it works is that the integral of U dv is always going to end up being equal to U times V minus the integral of V du. Now this pattern, we have to remember, and my very first year teaching this class, someone told me that she remembered it as U times V minus some voodoo. And that's how she remembered it. Like, it's U times V, that's the easy part, and then some magic happens over here, and that's how we get the rest of it. And that's how I've remembered it ever since. So hopefully that helps you remember it a little bit. So here's some tips for integration by parts. Typically, you're going to want to use integration by parts when you have something weird happening, some transcendental function like sine, e, natural log, something like that. So there is an element of guess and check here to decide what your u and your dv are going to be. So you're either going to choose u or you're going to choose dv. And so the first one part of it has to be u and one part of it has to be dv, but you can kind of decide in two different ways. You can either let dv be the most complicated part of the integrand, and you want to make sure that it fits a basic integration rule. Then u will just be whatever's left over. Because remember, it's typically easier to take a derivative than it is to take an integral. If once you choose u, you have to do du. So you're going to have to take the derivative of that. But when you choose dv, you're going to have to integrate it to figure out what v is. So you need to pick something that is easy to integrate. Okay? Or the second kind of category that you might want to think about is try letting u be the portion of the integrand whose derivative is a function simpler than u. You want to make sure that this factor is kind of going to go away eventually. Okay? So dv will be the remaining factors of the integrand. So let's look at just a couple of these for today to get us started. So we want to find the integral of 4x over e to the x. And you could kind of play around with this in u substitution, and you're going to realize very quickly that it does not work. So we have two options. We can let dv be the most complicated part of the integral, or we can let u be the easier part of the integral to take the derivative of. Also, integration by parts is always working with a product. So we need to rewrite this as the integral of 4x e to the negative x dx. So we need to split this into u times dv. Now, think about choosing something that's easy to take the derivative of. 4x would be very easy to take the derivative of. E to the negative x is also easy to take the derivative of, but think about what happens when you take the derivative of e to the x. You just get e to the x again, so it doesn't really get any simpler over the process. On the flip side, e to the x is very easy to integrate. So that's how I'm going to choose this. I'm going to let dv equal e to the negative x dx. You're always going to put the dx part with the dv because we want to be able to integrate it. Okay, and then I'm going to let u be 4x. So if I integrate both sides of this here, then I come up with v is equal to negative e to the negative x. Technically plus c, but we're going to just get that plus c at the end. So we're going to account for it later. Then if u is 4x, then that means that du is 4 dx. Okay, now we are going to take this integral And we want to think of it as 4x times e to the negative x dx. You don't necessarily need to write this out, but what I'm showing you here is that this part is u, and this part is dv. So we've accounted for all parts of this integral. So here's the rule. The integral of u dv is always going to be equal to u times v minus the integral of some voodoo, v du. Okay? So now we just substitute the parts. We've already defined all of those things over on the left. So u is 4x, and v is what we integrated. We got negative e to the negative x, minus the integral of v, which is negative e to the negative x, times du, which is 4 dx. So if we clean this up a little bit, we get negative 4x e to the negative x. We can pull out the constant multiplier, which would be negative 4. So that makes this plus 4 times the integral of e to the negative x dx. And that we actually already did when we did dv. So this all works out to negative 4 e to the negative x minus 4e to the negative x plus c. And that's it. That's our integral. This is how we use integration by parts, and I think it's so cool. It is just kind of like some magic happening. So again, the hardest part here is coming up with some sort of strategic process to determine what dv and u are going to be. And as I mentioned, there is a little bit of element of guess and check here. I can't tell you how many times I've chosen and realized halfway through that I've chosen poorly. And then that just means you know what not to do now, and you go back and maybe reevaluate what you want to choose. So here's some common scenarios where you would want to use integration by parts, okay, and some tips of how to set them up. So I would definitely read through that and see, because that'll definitely help you determine what you want to do here. So let's go ahead and look at example 2. We want to find the integral of x plus 2 times e to the x dx. So once again, this one is a little bit easier to decide what to choose. We want to let u equal something that's easy to take the derivative of and that is going to get simpler, or we want to let dv be something easy to integrate. So I think that the easy one here to choose, both of those cases make it pretty clear, I think. But e to the x is always the easy one to integrate. So I'm going to let dv equal e to the x dx. That means then that v is e to the x. And I'm going to let u equal x plus 2, which then means that du is just equal to dx. So once again, the rule is u times v minus the integral of v du. And so we plug in the pieces. So pause the video for a second and see if you can set this up yourself and finish this out now that we've defined these. I'll come back in just a couple seconds. All right, so u times v is going to be x plus 2 times e to the x minus the integral of v, which is e to the x, du, which is e to the x. And so we get x plus 2 e to the x minus e to the x plus c. And that would be fine, or we can distribute and combine like terms. That would also be fine. But that's the general idea. Now, think back to what we started with. This was not particularly difficult to use integration by parts, But did we really need to? That's the question that people always ask me about on this one. Because what if you distribute the e to the x? Well, then you're still going to need to use it because you end up with x e to the x for your first term, and u substitution is not going to help you there. So yes, we still do need to do integration by parts, and we end up with that answer there. Now, I love this example of finding the arcsine using integration by parts, because this is essentially how this formula was derived. So what we do, again, we need to decide, pick something that's easy to integrate for dv, or choose something that's easy to differentiate for u. And when we say easy, what we mean is we want it to get nicer. In this case, I would most definitely choose u to be the arcsine of x. Because when I take the derivative, it gets rid of the transcendental function altogether. We just get something in terms of x. So that's what I'm going to choose first. But then that begs the question, what's left to choose for dv? Well, we have dx left. So if we let dv equal dx, then that means v is equal to x. If you integrate both sides, the integral of 1 dx is just going to be x. Okay? So that works out kind of nicely. And then we need du, which is going to be the derivative of arcsine, which is 1 over the square root of 1 minus x squared. Okay, so now we need u times v minus the integral of v du. This is why you always want your derivative to work out a little bit nicer, because the u takes the ugly part and pulls it out of the integral. So now what I end up on the outside is the arcsine of x times x, u times v. So I'm going to write this as x arcsine of x. And then we can subtract the integral of v times du. So that ends up being x over the square root of 1 minus x squared dx. This integral now is something where we can just use u substitution. So now if I let u equal 1 minus x squared, du is negative 2x dx. So we have then, when we do this integral, we're going to need a negative 1/2 on the outside, and that ends up just being u to the negative 1/2 du. And that comes out to negative 1/2 times u to the 1/2, and then we have to divide it by 1/2, which ends up multiplying by 2. So that gets rid of that. We're going to get the plus c eventually, so I'm not going to worry about it so much here. We just end up with minus u to the 1/2. So when we go and put this all back together now, we have minus negative u to the 1/2. So this is going to end up being plus, x arc sine x plus u was 1 minus x squared to the 1/2, which is the square root of 1 minus x squared, plus c. That is the integral of arcsine. We can integrate an algebraic expression and get arcsine as the answer, but what this integration by parts does is it lets us integrate things like arcsine, natural log, things that we don't have rules, like general rules for, that what is the point of memorizing them when we could just use integration by parts here. So that's what I'm going to leave you with, the first 3 examples. That's enough to get you going. We'll come back and look at the other ones in the next video.